Hello, Martin. Thank you for your introduction, and hello, audience. I will indeed begin with my presentation as Martin introduced with what is hyperoxia, normoxia, hypoxia to cells, and why should you care about the oxygen in your environment. So first off, again, the webinar contents consists of the basics to a CO2 incubator, oxygen terminology, oxygen HIF1 alpha, a co-transcription factor, oxygen and its emerging role, and the future considerations for cell research. So, general basics about air and oxygen, because this is where it all starts off. Air, or dry air, by volume percentage, contains about 78% nitrogen, 21% O2, about a percent of argon, and less than 0.05% of carbon dioxide and other minimal gases. At sea level, you do also need to account that in the air there is water. And at sea level, on an average day, it's about 1% of humidity. In cell incubators, on the other hand, at 37 degrees, which is nice and comfortable for mammalian cells, CO2 levels have actually been raised to 5%, and passive humidity is kept at 100%. What does that actually mean for you? In cell incubators, that actually means that your oxygen levels are lower than this 21%. Why? Of course, 5% of the volume in the incubator is taken up by CO2. And this 100% humidity also takes up a volume of gas. And this remaining volume, the air, is then available for the cells, and also meaning the available amount of oxygen. But to better understand and define how much oxygen is approximately present in your incubator, we need to go over some basic physics. This will not include comprehensive calculations. We will just stick to the definitions of certain laws, constant, and very relative outcomes on those calculations. But to start off, we need to understand pressure to get a better idea of how to handle different oxygen contents. As you know, at altitudes, there is different amounts of oxygen. This actually means that although the gas composition percentage-wise is the same in the Himalayas as it is at sea level, approximately, the amount of oxygen present in the Himalayas is not the same as the literal molar amount at sea level. For that, you need to understand, of course, more mass on top will give you more pressure. And at sea level, air pressure is approximately 101 kilopascals. In medical terms, it's often the pressure used is millimeters of mercury or torr. Throughout this presentation, I will use the term millimeters of mercury. And in this case, the 101 kilopascals is approximately 760 millimeters of mercury. So at sea level, with 20.9% of oxygen, you would get to 159 millimeters of mercury partial pressure for oxygen. How this is defined, I will talk in a few slides based on one of those physics laws. But as an example, at an altitude of 500 meters, you'll lose a little bit of pressure. So you go from the 760 to the 313 millimeters of mercury, which would in turn mean that you have a lower amount of partial pressure of oxygen, 149 millimeters of mercury. This is already a slight difference of 6 to 7%. And as I say, the devil is in the details, and smallest effects can have large consequences. To illustrate this point of pressure and the amount of oxygen that you have available, on the right side you can see a graph showing barometric pressure versus oxygen content at different altitudes. So if you're doing a research in San Diego, which a lot of people do, versus having your same incubator at, for instance, Colorado or Denver, which is slightly higher than at sea level San Diego, you will have effects on your pressure and as such the oxygen content in the air. So air and incubator CO2 air. So we note the CO2, humidity, and the oxygen, the part where we're interested and talking about during this webinar. So as mentioned, relative humidity is kept at 100%. This is to prevent, of course, the evaporation of the cell media. Due to constants and calculations, at 37 degrees, the partial pressure of water is approximately 47 millimeters of mercury. Translate to a volume percentage, you go to 6.2%. In the incubator, as we know, and keep it at 5% CO2 to prevent acidification of the cell culture media due to a bicarbonate buffer, we know and can calculate that at 5% volume to volume, you would end up at 38 millimeters of mercury partial pressure for CO2. So as an intermediate, to get an idea and information from you as well throughout the presentations, there will be 4 polls. The first poll is a 2-tiered question poll, and I would appreciate if you could answer them. So the first question is, are you currently using an O2 regulated incubator? Basically it's yes, percentage based, yes, pressure based, yes, you do not know, or no. And the second question is, what models do you currently use or would be interested in using in contrast or in effect with regulating oxygen? Well, let's see, we're at 68%, so we're gonna end this poll. And then we're gonna continue with the presentation. As a backtrack to humidity, if you've ever been in the tropics, you would have noticed that humidity in the tropics can be very high and that breathing is a little bit more labored. This is due to a higher temperature, and with a higher humidity level, the amount of relative oxygen present is lower. How does this all relate to the physics? I wanted to put in a picture of Judge Dredd because physics rule. And with the physics laws, actually the first law that we need to pay attention to is Dalton's law. Hence, there's 4 Daltons. So Dalton's law of partial pressure will be shown, as well as Henry's law of partial pressure, the Bunsen constant, and Fick's law of diffusion. So Dalton's law of partial pressure states that a mixture of non-reacting gases, that the total pressure that they exert is equal to the sum of their partial pressures. So inside the incubator, we already mentioned the partial pressure of water, the partial pressure of the CO2, and that would leave at sea level with 670 millimeters of mercury pressure, 675 millimeters of mercury pressure, so 88.8% volume to volume of other gases, the air. So it's the original outside air of almost 21%. Inside the incubator doing the calculations, you would end up at 141 millimeters of mercury partial pressure for O2, which is then calculated to 18.6% O2 inside the incubator. So that is a near of slightly more than 10% difference between outside O2 concentration and the O2 concentration inside your incubator. Here is a graphic representation of the situation from an article by Werner et al., which I advise you to read. I found it very interesting to read and gives you a better understanding of what's actually on average happening in normal CO2 incubation cell culture experiments. So going from Dalton to Henry's law of partial pressures, getting from the gas to the liquid phase oxygen. So basically the law states that the amount of dissolved gas in the liquid is proportional to its partial pressure in the gas phase. Furthermore, you need to know the solubility or the Bunsen's constant, which is also temperature and liquid dependent. So the temperature, we know it's 37 degrees centigrade within the incubator. And because it's cell culture media, we just assume for simplicity's sake that it would be the same as blood plasma. And in blood plasma at 37 degrees, you have an oxygen dissolvability of 1.26 micromolars of oxygen per per millimeter of mercury pressure. And as you know, we have 141 millimeters of mercury partial pressure for oxygen. So at any given moment in an average cell culture media, you would be able to dissolve 177.66 millimolars of oxygen. And I say can. And why? Because Fick's law of diffusion. Because Henry's law is only valid in homogeneous liquids or in stirred liquids. Or in the case that the height of your media or the height of your liquid is not so high that passive diffusion cannot completely saturate it quickly. So normally, Fick's law of diffusion states that diffusion occurs from high to low proportional to the concentration gradient. O2 will diffuse based on Fick's law, and for simplicity's sake, as a rule of thumb, you can state that in tissues or in media, your normal passive diffusion range would be 100 to 200 micrometers. So in cell culture plastics, at least for my previous work, I know that my cell culture media height was at a minimum of 500 micrometers. And depending on how much you use, it actually might be much, much more. This would mean that your cells have lower amounts of oxygen present near them than that you're actually aware of. But there is a good side of it, because these cells are consuming the oxygen at the bottom of the well, basically functioning as an oxygen sink. And here on the right side, you see a graph experiment that shows on the x-axis the oxygen concentration and on the y-axis the depth. And due to this, the amount of cells, you can see that there is a steep gradient at a certain point, basically sucking the oxygen in the higher layers of the media down to the cells. As a side note, CO2 has a higher solubility, so there is no impingement there for CO2 not being able to saturate the whole media. But now to the practicality side of cells in an incubator. So you have the cells. We now know what the gas in the incubator does and how it's composed. We know that it's important, or it plays a role, the height of your media. We also know and understand that the amount of cells in your plastics will affect the oxygen diffusion in your cell media. So we have the passive diffusion, we have the one liquid phase, the media height that you're working with, but we actually have two gas phases. Because you have the gas phase throughout the incubator, and you have the gas phase, the head space of your cell culture plastics, which you also need to be aware of. Again, then we're switching to an audience poll. And the question here I would like for you to answer is, do you view oxygen as an important factor for your research? Thank you for answering these questions. I will now switch again back to the presentation. So next, why bother with oxygen? Well, we have a lot of research fields that are already focusing on oxygen, like sleep apnea, cancer cell research, pulmonary research with COPD and asthma, reactive oxygen species, of course, in muscle physiology, endurance exercise, general metabolism, for the brain, stroke or seizure, heart, infarct, basically the ischemia, reperfusion damages, and simple embryonal development. In vivo, O2 levels will affect tissue level on vascularization, blood flow velocity, cell type composition, even the microbiota in your gut, and during tissue damage, either due to injury or disease. On a cellular level, as mentioned, it will affect cell type, activation, proliferation, differentiation, and migration of cells. But cell and tissue exposure or access to O2 in a living creature is based on breathing this partial pressure of 159 millimeters of mercury, O2. And for humans, it has been shown that your lung cells, your alveolar tissue, sees about 100 millimeters of mercury, partial pressure O2. And this is due to your fresh air breathing in and mixing with your already oxygen content decreased outflow. So this amount is what's available to the alveolar cells, which is then transferred to the passing arterial blood, which then on average can have oxygen content between 75 and 100 millimeters of mercury. And going through the whole circulation, it will deliver oxygen. And then at the end, venous blood is seen having a content of 30 to 40 millimeters of partial pressure oxygen. But then again, we are incubating in vitro at a partial pressure of 141 millimeters of mercury, way more than the average cells see. As a practical example to this, I have taken an image from the article of Board et al., where he shows that the brain here, on average, under Normoxia conditions, as he's termed it here, sees between 25 to 50 millimeters of mercury, while under Hypoxia, damaging conditions, it sees between 18 and 8 millimeters of mercury. Again, same point, we're doing research for brain cells in an incubator at 160 millimeters of mercury. And as you know, hyperoxia is also a state and can be damaging. So we know that oxygen tension plays an important role in cellular functions. In vitro environments should therefore more closely resemble in vivo conditions. But of note is that tissue oxygenation in the brain or other tissues can be region specific. So it's not per se that the whole brain has one oxygen concentration rate. So although that is a limitation that we still have to work with, working under such high oxygen levels is definitely less preferred. But then I need to cut back and look at oxygen terminology, because in the previous slide we termed hypoxia, normoxia, and I mentioned hyperoxia. Medically speaking, hypoxia is defined as a deficiency of oxygen reaching the tissue of the body. And in its extreme form, where oxygen is entirely absent, the condition is called anoxia. Then I mentioned hyperoxia, which basically means there is an excess supply of oxygen present. And the term normoxia is very often used in the literature. Though it is not specifically and clearly defined, it is assumed as being the oxygen concentration at sea level, which is mentioned at 21% outside of your incubator. But if you do the calculations inside the incubator, it's actually 10% lower than you think what it is. So what is the relevance in relationship to your tissue and organs, your physioxia? Organs and physioxia. Many researchers have done oxygen concentration determinations throughout the years, throughout the different tissues. And here is a table showing some of these. I've highlighted 3 of them. For instance, physiological for kidney is at 72 millimeters of mercury. For the intestines, it's at 58. But for skin, oddly enough, it's at 8 millimeters of mercury. So if you think that under hypoxic conditions for a kidney, that could still be considered very hyperoxic for skin cells. So this is definitely something to consider when working with different cell lines and cell types, and how to evaluate what these specific cell types or cell lines view as physiological, hypoxia, and hyperoxia. Same question still remains: how to handle the incubator's hyperoxic, non-physiological relevant oxygen concentrations. So we come to poll question number 3. Do you believe it is good practice to regulate oxygen concentration in your experimental protocols? Well, I'm glad to see that most of you think yes, it's essential. Well, basically half of you have answered that it's essential. So now we will continue with the presentation. So what I would definitely prefer is that for future and for your self-awareness is that know and define what your normoxia and your hypoxia is in your research. Now, why do I say this? Because we are scientists and we would love to be the first to find new things, but we would definitely not prefer to be unique, because we need others to be able to reproduce our great results, to validate our findings, and for that we need to standardize. And for that, it's basically try to find a way to transition from percentage oxygen to either kilopascal or millimeters of mercury for partial pressure of oxygen. I mention this because it's the same as using for centrifuges RCF instead of RPM, because you don't know who's using which type of centrifuge, but everybody can install and define the RCF with their own specific centrifuges. But how do you have the ability to regulate your oxygen content? Because we do have the options already available for incubators where oxygen content is regulated. So culturing is possible, but you would also like to do your cellular handling in an oxygen regulated environment. For that, for instance, there is the option of using the Hypoxia lab, which is a benchtop option. As you can see on the right, it does not take up much space. So it's compact, efficient, gives you the ability to mimic through physiologia. And as an added bonus, for my most interesting part of this is that you basically can modulate oxygen profiles. So throughout a longer period, you would be able to go from high oxygen to low oxygen and have that as an added advantage instead of having a huge incubator only running at one specific percentage, or preferably in the future at one specific millimeters of mercury partial pressure of O2 rating. So physiologia versus hypoxia. How do cells actually know what the amount of oxygen is that they're seeing and how they're supposed to respond to that? So these cells do respond to hypoxic versus physiologic versus hyperoxic conditions. One of these main indicators that have been reported repeatedly is basically hypoxia inducible factor 1. It's a co-transcription factor which is often termed as the oxygen sensor of the cell. And why and how it functions. Here you see a graphical representation of HIF1 alpha in a cell, which is basically continuously being made and degraded due to the amount of oxygen present, allowing for PhD to label it and VHL to label it again, and for the ubiquitin protein proteasomal degradation pathway to chop it up. But then there is the case of the hypoxic condition. There is not enough oxygen anymore, so this protein is not degraded, allowing it to accumulate and move into the cell nucleus, where it can then drive gene expression. Here is an image I stole from the CAG database. The HIF1 signaling pathway, and as you can see on the right side, there are a lot of pathways related to genes that are being upregulated or regulated. I enlarge them, and you're basically talking about genes related to matrix and barrier functions, inflammation. Of course, the cell is trying to get more oxygen, so there is an increase in oxygen delivery gene expressions like EPO and heme, in angiogenesis, vascular tone, trying to become more efficient, so reducing oxygen consumption, promoting anaerobic metabolism, and attuning, regulating cell proliferation and apoptosis. But how quick are those responses of HIF1 alpha to changes in oxygen? Here are, in the next few slides, images from a publication from Joule et al. From 2001. On the x-axis, you see the time, and on the y-axis, you see the relative accumulation of HIF1 alpha. If you have the cells in culture and you move them from Normoxia incubator to an anoxic environment, you will see that HIF1 alpha stabilization takes about 30 minutes, and there is approximately, in this case, with a very large error bar, but nonetheless a 100-fold accumulation of your HIF1 alpha. How quick is that? Because I said the air in the incubator was switched. Well, the cells were put in an incubator with an anoxic environment. But in the cell media, you see that very quickly the amount of oxygen on the left y-axis rapidly decreases in almost less than a minute time. And you see that in 5 minutes time, the relative HIF1 alpha amount, the stabilization of it, increases to 7.5 to 10-fold in 5 minutes. So this means that cell media itself will also definitely play a role if you're working with oxygen-dependent effects in your cells. To more demonstrate this, if oxygen is dissolved in media, there is less oxygen dissolved in media that is warm. And on average, we heat up our media before we put it on cells to prevent a thermic shock, dissolving or removing a little bit of oxygen already. And if you're culturing with that, it is of course very handy to not bubble your media before adding it to cells, because you're basically reoxygenating your media. But the nicest thing would be, for instance, if you have a device that would allow you to deoxygenate your media and store it cooled, ready for use. And there we have our system, the Hypoxia for that. Because if this is already the graph where you have basically an environment of 0% oxygen. But if you're working with a 0.5 oxygen environment, you can already see that the relative accumulation in 5 minutes time is, say, 5-fold instead of 7.5 to 10-fold. So you can see that the amount of oxygen in your liquid will definitely have a significant effect on your HIF1 alpha presence, and thereby also directly in effect on your gene expression profiles. So now you did your experiments in your oxygen controlled environment in your incubator. You take your cells out. So basically you're in a few minutes, you're reoxygenating your cells. How quickly does that effect take place? Same article, Joule et al. Showed that You did before treatment, you did an hour of anoxic environment, and then you can see that after 15 to 30 minutes, the amount of HIF-1 alpha has returned to the normoxic situation. That does not mean that functional HIF-1 alpha is still present at 15 minutes. No, it's already being degraded, and it's just that you're already blotting for potential degraded non-functional HIF-1 alpha. So overall, it takes you about 30 minutes in an anoxic environment to stabilize HIF, and within less than 15 minutes, functional HIF is already starting to decrease. But then you would like to know how much oxygen is actually in my cell culture media or even in vivo present. And for that, I'm going to make a slight jaunt towards the in vivo situation, where you need to talk about free oxygen and bound oxygen in the blood. Because basically you have the dissolved oxygen, which is similar to the oxygen in your cell media. And in the blood, you also have the red blood cells with their heme and their blood bound oxygen. This is a formula that I got from a presentation from Gary Horowitz from the Beth Israel Dionysius Medical Center in Boston. And based on a few constants, you can see that the amount of dissolved oxygen in the blood is about 0.3 millimeters per deciliter, while the amount of oxygen bound to the heme on average is 19.6 millimeters per deciliter. So normal values are approximately 20 milliliters of oxygen per deciliter, but the largest part of that oxygen is bound to heme, and most systems use pulse ox method to determine how saturated your blood is with oxygen. But it is actually the free oxygen that can radicalize and do its effect in the cells. So for there is the role of the antioxidants to treat the free radicals. And that gives the additional focus on you need to determine preferably the free oxygen and not the bound oxygen. And there we have an option of using Oxylite System. The Oxylite System functions measuring oxygen concentration at the tip of glass fiber, and this measurement is non-oxygen consuming. So this is an added advantage that you're basically taking nothing away from the environment in relationship to oxygen to determine the oxygen concentration. Nice thing is also that this system uses the partial pressure method of determining the oxygen concentration. The system can both work in vitro and in vivo. That means, for instance, if you're using the Hypoxia lab, you can tie in this system and determine the oxygen concentration in your cell culture media or near the cells if you put the probe in, and know like, okay, my cells are currently experiencing this amount of oxygen. I know I can regulate the amount of oxygen in the air inside my working environment or the incubator. But with this system, you're able to also measure the amount of oxygen in your cell culture media. So I'd like to tie back into a few recent publications, and then we will do a summary and end with a Q&A session. One of the publications where, for instance, they use the Oxylite system by Seradin et al., they show that during wound healing, they're measured with the Oxylite at 4 different locations the amount of oxygen present. And you can see that during the recovery phase at the 4 different locations, the amount of oxygen is slowly increasing during the wound healing, and that has a effect on how cells are trafficking through the process of wound healing and how oxygen is tied into this. Another publication by Rohn et al. From 2016 showed that reactive oxygen species impair the function of hemopoietic progenitor cells generated from pluripotent cells. They used both chemical and physiological means to taper off ROS. And as you can see on the right side of the graph, the green bar and the bar just beside that show a comparable reduction in ROS in these cells. Nice thing is that this is done by switching from a 21% oxygen environment to a 4% hypoxic environment. Though of course you already know that 4% might actually be the physiologic, but the main thing for me here to focus on is basically you don't need per se to use chemical interventions which could potentially have off-target drug effects. Just working in an oxygen-regulated environment will give you the ability to affect ROS and other cellular processes in a more natural way. One of the more recent publications by Timpano et al. Shows cell viability in incubators regulated at different oxygen concentrations, ranging from 21% to 1% oxygen. And in this case, in this figure, it's clearly shown that 21% versus its top region, about 8 to 5%, that median cell viability is higher at 8% than at 21%. Clearly indicating that cells do prefer, even if they have been kept already for decades in cell culture, to be at their relative physiologic concentrations instead of the incubator standard Normoxia concentrations. And to at length discuss this, recently a review by Keeley et al. Has been published where they titled Defining Physiological Normoxia for Improved Translations of Our Cell Physiology Research towards Animal Models and Humans. And on the right side, you see two different graphs. The larger graph shows the amount of publications that have been clearly increasing since 2000 towards 2015 with topics of hyperoxia, anoxia, hypoxia, ROS. But the neat thing is that the physiological oxygen, which has been highlighted in the graph above that in the inset, has also shown a steep increase. So there is fortunately already a trend throughout the research field to aim to culture at physiologically relevant concentrations of oxygen. So my last poll for the day. My question to you, should scientific journals include guidelines for oxygen concentration to be included in the materials and methods section? Well, thank you for answering the last poll. And now we're going to go for a quick summary of this presentation. So basically, from percentage-wise oxygen description towards kilopascals or millimeters of mercury, what the oxygen content is in your incubator under most average conditions at sea level air pressure. What that means percentage-wise, that there is basically perception-wise a 10% difference. How this is easily depicted by the image figure from Werner et al. From 2015. The physics laws that explain how you go from the different oxygen concentrations from gas to liquid. How you need to keep in mind that you're basically working with two gas phases in your incubation system. Physiologia, you know what you breathe, you know then what your lung cells see in oxygen, and how you go from arterial concentration to venous concentration, And this difference is the amount of oxygen that the different tissues can have access to. An option to determine your local oxygen levels, and an option, of course, to work at an oxygen concentration controlled environment, and even a system that allows you to store your media in an oxygen controlled environment. So as a take-home message, for scientists in general, it's great to find new things. Please do not be unique. We would very much like to focus on reproducible findings that can be validated. So you need to ask for yourself, what oxygen concentrations am I currently culturing at? Do I need or do I want to regulate that? And can I improve my results by removing this oxygen variable? In another sense, it might also be very interesting to re-evaluate your previous results. Because based on some new publications, you might find a hidden gem in your old publications that could previously not be clearly explained, but now is possibly explained when factoring in different oxygen concentrations. So I thank you for your time, and I will now give back the microphone to Martin to moderate the Q&A session.
Thank you, Nikki, for that fantastic presentation. We have had some questions come through, which we'll get to in a moment. And we also have some questions that were submitted during the registration process. So maybe we'll start with those. And I would encourage all of you in attendance, once again, it's not too late to submit questions, so please do so through the Q&A menu. And we will answer any questions that we can't get to during the session offline, and we'll distribute the transcript of that Q&A to all of you in attendance. So Nikki, the first question is, if you have to take your cells out of the chamber to take an oxygen measurement, doesn't that defeat the purpose?
Short answer, yes, because as you've seen with the article from Jewel et al. As an example, oxygen is very quickly affecting cellular processes already on HIF1 alpha. So preferably, if you take the sample out, you will get an immediate effect on your oxygen concentration in the media and on the cells. So if you want to do oxygen concentration measurements, it is preferably done in a oxygen content regulated environment.
Okay. Another question is, I use a chamber that uses % oxygen right now. Are you saying that it cannot compensate for altitude and weather-related barometric changes?
Short answer is no, it cannot, but it's also in part dependent on how does your incubator actually measure its oxygen content and how is it attempting to regulate this. So for that instance, you really need to better understand your own incubator on how it's regulating its oxygen content. Percentage-wise, I would definitely say no with reference to barometric changes in weather, or even altitude changes if you're literally working in Switzerland in the mountains versus somebody in the Netherlands like me, which the half of the country is below sea level. So in that retrospect, you do need to account for the barometric changes, and if you work on % oxygen, it has been calibrated on something. And therefore, it's always important to understand how your system works, what it's calibrated on, and how it's attempting to regulate its oxygen content. So on average, I would suggest to try to see not percentage, but millimeters of mercury or kilopascals as the golden standard to work with in the future.
Okay. You may have answered this question during your presentation already, Nikki, but the question is, what about long-lived cells that have been growing in normal air for years? Will hypoxia still influence them?
Yeah, thank you for that question. And yes, indeed, I shortly touched upon that with the experimental work that I showed from the recent publication from in FASEP from 2019, where you show that culturing at different oxygen concentrations, you can clearly see there is a difference in cell viability. So as I mentioned, even if they have been cultured for decades already, passage after passage, being exposed to 21% between flipping fingers, yes, they are still responsive because you're talking about a relative versus absolute effects. Cells respond to relative changes, though they are situated in an absolute condition like this is a lot of oxygen, I can barely respond to this, or this is at a point where I'm very sensitive, I can have big responses to a percentage-wise small change in oxygen. So yes, actually the short question is, yes, the cells are still sensitive, but it would be better to research this sensitivity at a physiological relevant situation, like in the review by Keeley et al. Stated, to allow your cell culture work to be better translatable to the preclinical and the clinical fields.
Mm-hmm. Okay, thanks for that answer. Could we use a chemical method like cobalt chloride to induce hypoxia instead? And what's the difference between the chemical and the oxygen regulated method?
I always find that because in my lab where I did my PhD, I also did hypoxia research, and there they also used a lot of cobalt chloride in their research. And yes, there is a chemical method to mimic hypoxia, because that's actually what you're doing. You're trying to mimic a cellular response by inhibiting, preventing certain parts reacting with each other to stabilize HIF-1 alpha. But as everybody knows, using drugs will not only affect your target of interest, but has off-target effects. And yes, it can mimic, but it will have the off-target effects. So if you have the ability or the access to the option of regulating your oxygen content instead of using a chemical approach, every scientist would advise you to use that method versus a drug approach. But it is quite understandable to use this as an option in research field because not everybody has currently access to a oxygen regulated environment, but you do need always be aware of that this will not reflect the real situation as well as a regulated oxygen content could have.
Okay. Thank you, Nikki. I'm sifting through some of the questions that have come in. We have quite a few, and there are some really good ones here. So bear with me a second while I just do a quick read. Marta has asked how the partial pressures of the different tissues in the body had been measured. You had shown that graph of the oxygen levels that the different tissues and organs see. Can you provide a reference, or do you know much about how those values were determined?
Thank you for that question as well. And by head, I don't know how those specific partial pressures were measured, because some are of a conglomerate of many different publications where they did either electrically or chemically sampling and quickly determining the oxygen content, or in for the system that we provide, the Oxylite, you can literally insert your probe into the specific organ and do a close environment oxygen concentration determination. So there are definitely multiple ways of determining oxygen content, and they vary throughout the publications. And afterwards, we can provide you with some literature references to methods showing different organ oxygen concentration determinations. And otherwise, I would definitely refer you to the Keeley et al. Recent publication, because this is a large systemic review detailing literature publications on different organs where they mention the oxygen concentration determination with the specific references to those journals. So that will definitely help you with finding your organ or cell of interest and how the oxygen concentration was determined there. But I would definitely advise you to look at how they determine the oxygen and if that is a suitable solution for you.
Okay, thanks, Nikki. And I was going to say Nikki's email address is listed there. It's npansters@Scintica. If anybody has any questions or wants specific references, if they hadn't made a note, we can certainly send those to you. Nikki, Marta also asked, how long do the cells need to be exposed to be considered hypoxia? I think that's what's being asked. How long the exposure of hypoxia of the cell cultures should be to be considered as hypoxic?
Also a very valid question that you need to be aware of. I used the example of Jewell et al. In this presentation. I didn't mention the media height or how they even determine the oxygen. But you saw that in switching from a normoxic condition to the anoxic conditions within the first few minutes, the media oxygen concentration was already rapidly decreasing. But that is also in respect to how high is your media. Are you with moving the cells from A to B? Are you thereby, for instance, stirring the media, allowing for more rapid homogenization of the media towards the space, either the head space in your cell culture dish or plate, versus in the incubator? Or are you removing your plate, the lid, allowing incubator air to have direct access if you're doing short-term experiments? So how quick it happens? Jewell et al. Shows that in the maximum in anoxic situations, less than a minute, depending on your medium height. In other circumstances, I would advise you to find a way to determine your oxygen concentrations if possible and do a time curve experiment. Because what you are doing in your lab may not be exactly the same as what your neighbor is doing at sea level or somebody doing research in the Himalayas is doing, as extreme examples. So how quick? I would say even less than a minute could be possible, but it's very much dependent on your media height. For instance, in a 96 well plate, media height is, well, roughly 345 millimeters versus a 35 millimeter dish, you're talking about 500 micrometers. Although a larger surface area, one swig will stir the whole thing, you can't do that in a 96 wells plate. Their passive diffusion will be the main defining part in how to homogenize your oxygen content in the media. Long answer, and I hope that the first few sentences already answered your question.
Perfect. Yeah, thank you for those questions, Marta. Okay, Connie asks, and again, we may not know all the answers to these questions. We'll try our best, and what we don't know, we'll certainly find the answers to. And hopefully I don't put you on the spot here, Nikki, but how do oxygen levels differ between adherent versus suspension cell lines?
Yes, that's it's not so much the oxygen level, it's the pericellular oxygen levels what I think Connie is referring to. And it's more difficult to determine that in adherent cells versus suspended cells, because often in suspended cells, unless you're using a two-tiered cell culture media and thereby calling it suspended cells, are often in motion. So due to the motion, you're more likely to be working with a homogenized cell culture media. So Dalton's law and Henry's law are more applicable. You don't need Fick's law of diffusion. So there is definitely a difference, and there will be less oxygen available at the bottom of your plate or whatever you're using to have your suspended cell lines in than at the top, but the difference will be less. your overall average will be higher than in cases of adherent cells on average medium heights, where Fick's law of diffusion will play an important role on how much oxygen will your cells see. So there will be a difference, but I cannot tell you the definitive number on this.
Okay, perfect. I know, Nikki, you also have access to some of these questions. If there are any, we're almost at the end of our hour. I think maybe what we'll do is we'll just go one or, a few minutes late. Again, for those who can't stick around, we will be answering these afterwards. But let's see here.
Well, we have, for instance, a question from Steffi. She asks, yes, you mentioned two gas phases, outside and inside the cell culture plastic. So how fast does diffusion occur between the two phases, and what is the approximate oxygen inside a flask that is already located inside a oxygen-regulated incubator? I have not found any reports on that in the literature. So this is something you really need, or I should have actually done myself experiments using the Oxylite system, for instance, to do measurements in air, but that's more difficult to do in the incubator, because as soon as you take out the lid and do the oxygen measurement, you're already disturbing and mixing your air concentrations. There is a difference, passive diffusion, because you're basically working with stagnant air in a culture flask or in a lidded Petri dish style option. You're working with passive diffusion. There is some air stirring in the general incubator, so air movement will result in gas mixture, but it is slow. So we're talking here not in minutes, we're talking here potentially hours. So that is something you need to account for. And for those that are interested, maybe make a measurement of what is the oxygen content in your headspace. As a side note, there are already also articles and reviews mentioning, please be aware that plastic, it's not so thick that it does not allow oxygen to penetrate it. And there are even companies working on plastics that allow oxygen diffusion. So to circumvent the problem with oxygen access through the cell culture media, they allow oxygen to diffuse through the plastics from the bottom up. And the other way is the insert cell culture option, where you basically have your cells on a separate disk hanging in your cell culture media, elevating your cells towards a slightly higher level, giving them more access to oxygen. So that was in addition to asking the question about the two phases. It takes a long time, especially in a large flask, to get an equilibration in your flask versus your outside oxygen content. I sometimes even left off my lid in my cell culture or on my dishes to have immediate access to oxygen. Though that really depends on how clean you and your colleagues are culturing in your cell culture environment, because doing this will set you up for infections, definitely.
Okay, Nikki, let's ask one more question. This is a product-specific question. Sonner has asked, where is that question? It's related to the Oxylite.
Ah, yes.
They're asking whether it can be used in fluids like cerebrospinal fluid, amniotic fluid, and can the probe be used in tissue in vivo? Can you just talk about that a little bit?
Shortest answer possible is yes. Yes, you can use it in different liquids, and yes, you can use it in vivo. I don't know if you wanted to use it in humans, then the answer is right now no, for as far as I know at the top of my head. There has been more than enough publications referencing the Oxylite system where they use it in vivo on animals to determine oxygen concentrations in brain, cartilage, different organ types, or even in muscle where you do clamping experiments to see if remote ischemia reperfusion can help with cardiac ischemia events. So I hope that that answers your question if in different fluids you can do the oxygen concentration determination. And yes, you can definitely use it in vivo.
Perfect. Perfect. Okay, well, Nikki, we've exceeded our 60-minute mark for the session today. So I think to be respectful of everyone's time, we'll wrap things